Hello everybody. These days, as we are working out of our institutes and labs, I will make my story from here. I'm Filipp Kornеев. I am an associate professor in Department of Theoretical Nuclear Physics in National Research Nuclear University MEPhI. Our department is a part of Laplace. Laplace is a strategic academic unit in the university, which is the Institute for Laser and Plasma Technologies. Laplace gathers a lot of departments which are related to lasers and plasmas and to different applications which are connected somehow to lasers and plasmas. We have a lot of educational programs which allow us to prepare good specialists in all directions which are somehow connected to these lasers and plasmas physics and of course applications. And what I should mention here is one of the a key project of our institute. It's MEPhI. It's a big kilojoule class laser system, multi-beam laser system, which will allow, when it will be constructed in maybe a few years, allow a lot of possibilities in research and in preparation of good specialists in physics, in experiments, which can these specialists can make then experiments all over the world. Of course, our department, as it is theoretical department, have a lot of theoretical areas, and a lot of different groups are working in different directions of theoretical physics, including nuclear physics, solid state physics, light propagation, and so on. But as we are part of Laplace, we have a lot of publications and a lot of groups which are working in laser plasmas. And so do I. So I will go now to my presentation. I will make presentation to explain what is magnetized laser plasmas and what you can do with magnetized laser plasmas, and how you can optically, so with lasers, with laser systems and laser huge amount of energy in laser beams, produce magnetic fields. And this is topic which I devoted last 5 years of my work. So I will go, as it is starting to snow a little bit. So see you in few seconds. So I start my presentation. It is entitled Magnetized Laser Plasmas, the Universe in a Focal Spot. This title means that when we have very intense laser beams which are focused into quite small space, we can produce very hot plasmas, and these plasmas have very high energy density. In some situations, this high energy density can be compared to astrophysical objects, and we can model and study then some phenomena which we can observe in space with telescopes from Earth or from spacecraft. So now let's look on different scales of magnetic fields. Starting from very small fields, about 10⁻15 Tesla, we go up, then we go to the Earth magnetosphere, which is about 10⁻5, 10⁻4 Tesla. Then we skip several orders and come to several Teslas. So several Teslas corresponds to constant magnets, which we can find in shops. We can buy it and feel what is magnetic field strength of 1 Tesla, how it looks like. Several Teslas correspond to sun magnetosphere, for example, and different other stars. And several tens of Tesla, it's a field which are used in different devices, like in medicine or somewhere else. And it is a scale which we can achieve by using some discharges of electric current produced using the capacitor banks. Then again, skipping 2 orders of magnitude, we go to this value, 1.72 kilotesla. It's an atomic field. So this is a field which corresponds to interaction of electron with nuclear in atom. And this range, about several kilotesla, it's a maximum magnetic field which we can achieve now in laboratories, and actually we can achieve it with lasers. I will speak about that later. Then when we go further, we go to very intense magnetic fields, which comes from 10 to 6 to 10 to 13 at least. And this field corresponds to neutron stars. So why it is so interesting, and which is our motivation for studies of magnetized plasmas? It contains both fundamental studies and applications. In fundamental studies, of course, it's different astrophysical phenomena like sun, like stars, like cosmic rays, shock waves, astrophysical jets, and so on. Also, it's very interesting to study matter properties in strong magnetic fields. It's atomic physics and nuclear physics, it's condensed matter quantization, and so on. And as for applications, we know that particles can be guided and accelerated by strong magnetic fields changing in time. Magnetic field can help to produce some types of radiation. It can be used for creating some nozzles or plasmas. It can confine plasma, and it can be used in magnetized inertial confinement fusion, for example, to suppress electron thermal conductivity. It's used in some novel schemes. It's used for electron collimation and fast ignition, and so on. As you see, it's quite a lot of different problems and possibilities to study with laser plasmas. From astrophysical point of view, there are 2 images on this slide. The left one, it's a jet, and the right, it's expansion of supernova remnant. Both images are obtained with the Hubble Space Telescope. And in principle, these effects, these phenomena, also like some different ones, because it's not, of course, not all which we can observe, can be modeled in laboratory. So in lab, we can produce collision of plasma flows, we can study plasma in magnetic fields, we can study evolution of plasma structures, and we can model astrophysical shocks. Now I switch to generation of magnetic fields with lasers. And first, let's look 50 years ago, and we can see at least 2 propositions how to generate very strong magnetic field. The one proposed by Sakharov was to use explosives to compress the magnetic flux. Initially, the magnetic flux is created here, and when you implode it by some explosives, then it is compressed up to several thousands of Tesla. Up to 3,000 of Tesla was produced in such devices. And the other one was using of lasers. So here in this proposition by Koropkin and Motylev, you can find that they estimate that if you use some intense laser beam and irradiate the coil, the current here, which appears by this irradiation, can drive the coil so that you achieve the magnetic field up to 1 kilotesla. So what we have now? Here on this image you see the photo of a real discharge coil which is used in experiments. This coil can produce a magnetic field inside of the order of several tens of Tesla up to 40 Tesla, and it is a limit because if you produce a stronger field, then the magnetic pressure is so high that you just explode the coil. So with this range it's a non-destructive generator. If you go upper, it's a destructive generation and you explode all the chamber, experimental chamber. The magnetized volume is about 1 centimeter cubic, and the time scale is about 1 nanosecond of the magnetic field. So in this device, the minus it's that it's necessary to have very large capacitance bank to drive the current, and it's very limited in space for diagnostic, for example, because if you have some holes in this coil, you can use optical diagnostic, but you cannot add anything inside because it's only few millimeters. It's about 1 cubic centimeter of the volume which you can operate. But in the plus side, you have a stationary in time and space magnetic field distribution, and it's quite constant during the laser timescales. Here is one of the examples of how this coil can be used in experiment. This experiment was devoted to studies of plasmas which interacts in magnetic field. The two plasma flows which were created by intense lasers, you see in this image from left and right, two laser beams irradiate two foils, and plasma goes from the foils inside the volume which is occupied with the magnetic field about 20 Tesla. So this magnetic field is compressed, as you see on this image from simulation. So this rho is a magnetic field and it is density of plasma. The magnetic field is compressed, and then there is some evolution of magnetized plasma inside, which finally result in stagnation of plasma between the two foils, and it is absorbed in diagnostics, like here, what you can see on this lower row. Without magnetic field, it was also obtained some data and it's consistent with the simulation. There is no stagnation of magnetized plasma. So it is one of possibilities how to model the plasma evolution in external magnetic field. What we can make with the powerful lasers in terms of magnetic field production. After chirped pulse amplification invention, the laser technique was developed to the very high energy density level. And now we have a lot of different optical schemes for magnetic field generation, which can be combined with many other laser-driven studies. For optical magnetic field generation schemes, we can mention that we have very high energy fluxes available. The magnetic field energy density is increased by decreasing magnetized volume. We can produce magnetized collisionless plasma, which is non-trivial, and it is quite cheap. It's a single shot scheme usually, but it's quite cheap because it's very small. It's not dangerous for chamber, and then we can produce quite complex magnetized structures, but it's rather sensitive to experimental parameters. It's not very stable, and it is normally not stationary at laser timescales. Along with the production of magnetic fields, we can produce with lasers a lot of different kinds of objects. For example, we can produce fast plasma in particles flows, and we can do it even in relativistic regime, and even electron-positron flows available now. Diagnostic with lasers, it's very wide. It's optical diagnostic, it's proton deflectometry, and a lot of different other types of diagnostics. We can produce quite complex time-dependent plasma structures with laser pulses. We can go to quantum electrodynamic regime. And one thing which we should mention here is that we don't have gravitation in laser laboratory. The general principle of production of magnetic field is to collimate a current. Consider these two situations. In one situation on the left you have current which is isotropic. So you have, for example, electrons which are going in all directions in the same way, and in this case you don't have flux, you don't have a directed flux of electrons, you don't have electric current which in average can create any magnetic field. But if you can create a directional flux of electrons, then you create directly magnetic field around this current. So the idea is to create some anisotropy in laser plasma interaction to create magnetic field. The anisotropy can be created by some wire, for example, like here, and this wire can be of a strange shape. If you propagate electron current along the strange shape of this wire, then the magnetic field will have also some strange structure, so you have a lot of freedom here. Now I show several kinds of devices, of schemes for magnetic field generation with lasers. On the left here it's a Biermann battery effect. It's caused by non-collinear gradients of temperature and density in plasma which is created by laser radiation. Here is a typical scheme. This is expanding plasma, and you see that there is a magnetic field which is around this plasma. The next picture corresponds to the current of fast electrons. So again, this is a shape of the expanding plasma from the target, and in some cases when you have some parameters which allow hot electron generation from the target, these hot electrons, it's just a current which creates a magnetic field around them. So you can create then magnetic field around this current, and then this magnetic field is frozen inside the expanded plasma here. Then here it's what I will show in more details below. So it's plasma which have some special structure. It can be created by laser beam with a structure which corresponds to rotation of intensity, for example. It can be created by plasma waves with similar structure, and schematically it is indicated by this spiral which corresponds to some intuitively related to rotation of some energy density. Here in this row, all of the devices correspond to different discharges. Here it's a standard. Now this scheme is used very often. So this is a standard scheme which is called capacitor coil target. Here is a capacitor and here it is a coil. It is a modification of this capacitor coil targets, just quite small, smaller than this, and it is also more compact. Then it is a snail target where you have the laser propagating inside and you create the discharge here. I will show more details about that below. And the chiral structure, which also can facilitate the current, rotation of current and the magnetic field which is created inside this volume, inside this target. So what is here? Here it's intensity of laser beam which has orbital angular momentum. This is intensity of this beam, and on this row you see the projection of electric field. This is longitudinal, radial and azimuthal projections of electric field in the beam. So it is rotating, and in this propagation the laser, the light, carries orbital angular momentum. So it has some internal rotation. What happens when it interacts with plasmas? It happens that electrons are rotated by this laser beam, and finally they achieve orbital angular momentum, which is indicated here. So this is L. L, it's orbital momentum of electrons. This line, dashed line, is the maximum of laser intensity, and as you see here, electrons are rotated in one direction inside this area, which result in its turn in generation of magnetic field, because when you have rotation of electrons, it means that you have the solenoidal-like current, and inside this current you have, of course, magnetic field flux. The two images here and here correspond to a different orbital angular momentum of light, which means that you rotate electrons in one direction or in other direction, and then you generate by laser you generate magnetic field of different directions. But it is not necessarily laser light which should carry orbital angular momentum. It can also be carried by plasma wave itself. On this image you see the deviation of density, which has positive and negative spirals. So the spiral structure means that you have some internal chirality which is attributed to magnetic field, and indeed this deviation of density creates the fields which can be indicated here, and you see that you have the magnetic field along this axis, and also you have the azimuthal magnetic field B theta. Even more effective magnetic field generation can be achieved in these structures if we consider a Landau damping effect, where we observe resonance between particles and wave, particles for some special parameters for velocity and direction of their motion. Then we can find that the orbital angular momentum from the wave also is transferred to resonant particles, and this particle can be effectively accelerated in some special directions, which is can seen from these plots. So for different orbital angular momentum, we see that p theta is increased while px so it's along the axial direction, is decreased, which means that particles are rotating, and of course this rotation finally will result in very strong magnetic field generation. Now let's turn to capacitor coil-like targets. Here I present you the results of simulations. So it's a long target with a coil here, and laser interacts with the upper side of the target. Then a discharge is generated. On this set of images you see that this discharge propagates along the wire, it propagates down, and finally it goes through the coil. Here on this image you see that inside the coil the magnetic field is generated. A very important feature here is this length of the discharge. We have an important discharge parameter, which is relation of this discharge length to the length of the target where we want to generate the field. If this relation is very small, it means that we have only propagation of the small peak of discharge along the contour, like here, and it is not very efficient for magnetic field generation. But when this length is small and the discharge is very long, then we have almost a constant current which flows down, and we have a very long current generating magnetic field in a constant way. So it means that we have two different scenarios of magnetic field generation in capacitor coil targets. Here I present you the conventional, so-called conventional means that it is already used for different types of experiments and it is very efficient. Capacitor coil target, where you have the capacitor here, the laser goes inside, it generates very hot electrons which goes outside this internal disk, and the current is connected by the external disk here, and another part of current goes here. So it is connected like this, here and here, and for efficient working of this target, the laser should be quite long. The laser pulse here should be quite long. But if you want to use very small, very short laser pulses, which has higher intensity, for example, then it's just possible to decrease the size of this target and go to the scale, like here, for example. It's a micro scale target, so it's about several microns in each direction, and in this case it's possible also to generate magnetic field using femtosecond lasers, which is quite efficient. So you see that it's in these units it corresponds to tens of kiloteslas inside. Now consider different types of discharges. It's so-called targets with high self-inductivity. One of the examples of these targets is targets with internal chirality, like those which you see here on this slide. And the idea is that in this target you put laser beam inside, and laser beam interacts with the surface of the internal surface of the target, and electrons are escaped from this surface. Then the discharge currents are generated along this close, and because of this shape you have finally the rotational current, and this rotational current generates the axial magnetic field. Indeed, we can see in these pictures, this is simulations, but we already have experimental results, that when we interact with lasers, this internal shape of the target, the strong currents are generated, and these strong currents are shown here with the arrows on different times from here to here. The magnetic field inside, which is on this column, is grown up, and finally we end with this magnetized structure. Very strong magnetic field inside, and the opposite field in these areas, because we normally tend to have the total magnetic flux conserved, and this shape, this magnetized structure is stayed there for a long time actually. And another example is a so-called snail target. So it's something like a cylinder which is deviated from cylindrical shape so that you can put laser beam inside. How it works? When laser comes inside, it propagates along the surface like a whispering gallery, and it creates a current of electrons which goes along the surface. It's this dashed line, and also it creates a return current, and between these two currents, which are indicated here, the plasma is strongly magnetized, but it is dense plasma, and because it is dense, it is collisional, and magnetic field can be penetrated inside. Then this magnetized plasma expands, it expands inside, and finally it creates the theta pinch-like structure. Here you see the simulation, the animation, which shows how it goes in time. On the left image it is a magnetic field, so now the laser beam is already stopped. The plasma expands inside. What you see here now, it's a creation of this theta pinch-like structure. It's theta pinch-like because the density in the region of high magnetic field is less. So the pressure balance, pressure between plasma and magnetic field, create this surface where the magnetic field and plasma density are separated. You see that it is very stable, so it's almost nothing happens. Now it's stopped, but we see, and I will show later, then it stays for a very long time in experiment. Here it's a pressure balance equation, which I already mentioned, and on this plot you can see that efficiency of the magnetic field generation, it's about 5 to 10%. So this level indicates the energy of magnetic field, and this is the highest energy in the simulation box. The relation between these two values give this efficiency in energetic scale. Now we have experiment results on that, and first of all we have the features which correspond to magnetic field, because when we rotate the target we see that this feature is also rotated, which means that of course that it is the dipole structure of the field. And also we see that this time scale for this structure is about more than 100 of picoseconds, while the laser itself, the laser duration is only half of 1 picosecond, which means that this is the very stationary structure and the plasma is magnetized, because if it would not be plasma, then nothing can contain the magnetic field for so long time. And with a different setup, with the different parameters, we see this magnetic field in optical diagnostic. In this case, we have the magnetic field which is compressed by the expanding plasma from the surface of the target, and it goes that it comes from 8 Tesla in 183 picoseconds to 40 Tesla at 368 picoseconds, which means that it is compressed in this duration from this to these times. Should mention that it is another laser beam which is quite long, and in this case we did not measure the stable structure for a long time, because in this optical diagnostic it is impossible to see something which is very dense. Now I will show you two examples of how laser plasma experiments can be related to astrophysical studies. The first example is interaction of plasmas which contain Biermann battery fields. The experiment was held by a group of Chikan Lee at Omega Laser Facility in 2018. It's published in this paper. The idea of experiment is interaction of a plasma jet. A plasma jet is created by irradiation of hemispherical target here. Interaction of this jet with the gas bag here. So it's a plastic shell like a ball filled with the gas. And during this interaction, plasma which expands from these heated regions of a gas bag and plasma which expands from this hemispherical target as a jet, both contain Biermann battery fields, magnetic fields. So it's interaction of magnetized plasmas. In diagnostics, the images here on this row, it's diagnostic images obtained by proton deflectometry. So in this diagnostic, we can see that interaction region has a filamentary structure. This filamentary structure is related to some instability which is generated in the region of interaction of two magnetized plasma, and it is interpreted like a shock, at least a shock formation. Also in other diagnostic, this is confirmed by the density measurements and by reconstruction of magnetic field here. What we see in interpretation of this experiment obtained by simulations. In simulations, we see that magnetic field in the plasma, which initially had some magnetic field in it, in interaction is compressed, but it is compressed in electron subsystem. The ion subsystem goes through this region of compression magnetic field because magnetic field is not strong enough to deviate ions, and the ions which propagate inside the secondary plasma create this filamentary structure. It is viable filamentary structure. So in this experiment, we probably can see two shocks, or at least formation of two shocks. The one shock is a magnetized shock which is created by so-called magnetized piston, and it is just a magnetic field which top electron subsystem. And another shock is a collisionless shock, which is created by generation of Weibel instability. In simulation, we can see at least at late times, probably it was not observed in experiment, but it can be observed if we have more energy and more time, that these two shocks are separated. Also, it's very interesting that in experiment and in simulations, we see that we have non-thermal particles which are coming from the interaction region. So these images here indicate that we have a non-thermal tail, so-called tail of particles, and the same or very similar tail is extracted from the simulations which are presented here. So it is one example, and this example refers to interaction of two magnetized plasma, almost collisionless, or at least with some efficient collisionless mechanisms, and it can be scaled to some astrophysical phenomena. Another example. This experiment was held in Osaka in the Institute of Laser Engineering at LFX laser facility. The idea of the experiment was to study magnetized plasma interaction inside the volume of snail target. And in this experiment, as you see, this is a setup, experimental setup, Banov diagnostic. The proton deflectometry showed the magnetic field inside the snail target by the imprint on this RCF stack. It was also RCF stacks along the axis of the target to measure spectra of particles which escape the internal volume. Inside the target, the plasma was magnetized in the way that the two oppositely magnetized plasma with very high magnetic field interact with each other. It was done by putting the laser beam so that it touch also the opposite side of the target, as you see here on this image, and the current goes not only in this area but also in this. Then the plasma expands from both of these sides with opposite magnetic fields, and on this image you see the structure of magnetic field, the negative and positive magnetic field inside the target volume. In the interaction region, here the reconnection phenomena was observed, and in this reconnection phenomena, acceleration of particle was created and measured. Here you see the spectra of these particles which escape the interaction region. On the left column it's a proton spectra, on the right column it's electron spectra. Here it's experimental data, here, and here the simulation data. You see that it is quite similar both for protons and electrons, though for electrons it is more similar than for protons, but in both situations a very hard tail was observed. For electrons it was 1.5 approximately, so it is a power law of the spectra here. And for protons it was slightly different. It was for simulation it was two types of spectra, 1.5 and 5.5 approximately, and for simulation it was one was 3 and another was 17. So it was different, but it can be explained by sizes of the interaction in simulation and in experiment. The interpretation of the data, experimental data, shows that in this experiment plasma had parameters which are very similar to the parameters of a binary system. For example, Cygnus X1 has a magnetic field in the magnetosphere about 1 kilotesla, while in laser-driven snail it was 3 kilotesla approximately. The density is also very similar. You see it's about 10 to 24 in cubic meters. The temperature and magnetization parameters, which are here, were also of the same scale. This means that in experiment we can produce a plasma which has the same parameters that in a very far astrophysical object, a binary star. But, of course, it was only in a very small microscopic object. And finally, I conclude my presentation. The laser system now allowed to produce very strong magnetic fields as they are the most powerful energy sources. The hot magnetized plasmas in laser laboratory are available and its parameters can be varied in very different ranges. Plenty of high energy density applications can be developed and are developing in modern laser laboratories. And one of the most attractive and very interesting fundamental applications is the modeling in a micro volume of laser-matter interaction, scaled or even realistic astrophysical plasma interaction. Thank you for your attention.